Hello friends, today I will be talking about the topic organic stereochemistry. This is an important topic for class 11, 12, JEE, Main, NEET, GATE and other competitive exams, and also for UG and PG chemistry students. And surely you will get questions common from this chapter in any kind of chemistry exam paper. And today I will be focusing specially on RS nomenclature, and I will tell you some easiest trick so that you can score full in the exams. Before we move further, we need to focus on, or we need to understand one point around which the whole concept of stereochemistry develops is chirality and optical activity. When a carbon atom bonded to four different groups could lead to optical activity, and the center will be called as stereogenic center. As you can see in the example, the carbon atom is attached with four different groups here: hydrogen, hydroxyl group, methyl group and ethyl group. So all the four attached groups are different, and therefore the carbon center is a stereogenic center. In general organic compounds, any lack of plane of symmetry lead to optical activity, and the compounds are known as chiral compounds. Here two examples are there. For example, one cis 1,2 dihydroxycyclohexane and trans 1,2 dihydroxycyclohexane. Now in case of cis isomer, you can see there, you can imagine a plane of symmetry passing through or in between two hydroxy groups, dividing the whole molecule into two similar halves. So there is a plane of symmetry in that molecule. Whereas in trans isomer, there is no point or element of symmetry in that molecule. So that's why the cis 1,2 dihydroxycyclohexane is an achiral molecule and the trans isomer is a chiral one. Now for optically active compounds, they can exist as enantiomers. Now the enantiomers are mirror image isomers to each other, and they are non-superimposable to each other. Now before we move further, we need to understand a quandary, or rather say a practical dilemma, that how do we name the enantiomers. Here in the structure you can see 1-bromo 1-chloroethane and two molecules of that, A and B, which are mirror images to each other. However, they are not exactly the same and they cannot be superimposed on each other. So those stereoisomers of A and B are known as enantiomers. Better understanding can have, for example, if we look at the point B, the achiral objects which shows two flasks, conical flasks, which are mirror image to each other, and when you bring one image on the other molecule, they are completely superimposed. So those molecules cannot be the enantiomers. Whereas for the chiral objects, for example, it's been taken as a left hand of human being and the right hand of the same human being, of course. So they are mirror images to each other. However, they cannot be superimposed. Now here, one thing need to be mentioned or remember, that when you or we talk about superimposition, the hands, for example, the left hand should be picked up and put on the right hand in a fashion you can see in the picture in the right hand side, so that the thumbs of both the hands pointing in the outward directions. So that means they are non superimposable. So this is a general concept need to be developed, because in most of the students the concept of superimposition lacked. Here I will discuss about one more example, that is cis 1,2 dichlorocyclohexane. In the green isomer and the purple isomer, you can see they are mirror image to each other, and also it is possible that the green isomer of cis 1,2 dichlorocyclohexane can go on ring flipping, and further 120-degree rotation will lead to the purple isomer, which is the mirror image of the green one. Now if the enantiomers are in equilibrium with each other, through the ring flipping, one enantiomer cannot be separated from the other. This need to be remembered. Similar way, trans 1,2-dichlorocyclohexane is another topic showing the enantiomers and diastereomers in terms of concept development. The green isomer and the purple isomer, you can see they are mirror images to each other. However, they are non-superimposable, which are shown in the top. So those two stereoisomers are named as enantiomers. Like if you can think of the enantio cats, you can see and look at the legs of the cats, and you can see those are the mirror images, and when you superimpose one over another, they don't superimpose, so they are non-superimposable one. However, if you go on ring flipping of each green or purple isomer, you will end up with another two stereoisomers, which are also mirror images to each other and non-superimposable to each other. So they will be enantiomers in relationship to each other. And now if you look at the left side column, from the green one, after ring flipping generating the purple one, they are having no mirror image relationship. For example, in the right hand side, you can see the picture of two cats. Those are named as diastereo cats, where if you look at the color of the legs of the cats, they are not equal, and therefore they are not having any mirror image relationship. So those kind of molecules will be termed as the pair of diastereomers. Here I have shown some objects which we usually found around us, uh, which are chiral and achiral, and still we don't look into that in that way. For example, the glasses, those are achiral until you marked the glass, and because they are superimposable to each other. Now if you mark one of the glasses, you can see these are non-superimposable to each other, the mirror images, and therefore they are termed as chiral molecules. Similarly, for screw that we use in the carpentry or other purposes, they are mirror image to each other. However, they are non-superimposable. Whereas we can see for a butterfly, there can be imaginated a symmetry plane going across the butterfly. Now, if you take the mirror image of the butterfly, that will be a superimposable object. Similarly, the other achiral or non-chiral molecules like the bottles or the circles, cars, uh, tissues, those are the non-chiral or achiral molecule. Whereas if you see regarding our hands, similarly our feet, those are non-superimposable mirror image isomers. Those are enantiomers. So those are chiral objects. So next I will be moving into the absolute configuration and the Cahn-Ingold-Prelog rule, very important one. And as I said, with the quandary, a solution to this quandary was proposed by Cahn, Ingold and Prelog in the year 1966. And the very famous CIP rule, the resulting CIP protocol, works as follows. We need to memorize only 3 points. Those are the most important points you need to memorize, and then it will become easier to assign the stereochemistry of a molecule, especially the RS nomenclature, those things. First, it says that we need to prioritize the 4 groups around a chiral center according to atomic numbers. The highest atomic number is assigned the priority 1, and the lowest atomic number will be assigned as the priority 4. Second one says that we need to orient the chiral center in such a way that the priority 4 group or the substituent is pointing away from the viewer. So it should be, if you are looking at the screen, it has to be away from the screen, that is, it has to be behind the screen. So for this purpose, it is usually we say that the substituent which is attached, or the fourth substituent, need to be attached using a dashed bond. And then the important one, that we need to trace the path of the priority substituents in order to 1, 2 and 3 And if we have kept the priority 4 group in a dashed bond that is away from the viewer, then we don't need to take care of priority 4 group anymore. And when we trace the path of 1, 2 and 3 substituent, then if the path traced from 1, 2 to 2 to 3 is clockwise, the chiral center will be assigned as R. Now this R term is a Latin one and it means rectus. Okay. Again, if the path traced is counterclockwise, the chiral center will be assigned as S, and in Latin it is from sinister. Now we have a better way to describe the molecules A and B as I have shown before, and the molecule A will be termed as R1-bromo-1-chloroethane and the molecule B should be named as S1-bromo-1-chloroethane. And however, before I move into the discussion with details with the RS nomenclature, I would like to share you the look at the priority order of some different groups. Here you can see the different groups are assigned over here, and the Cahn-Ingold-Prelog priority rules are used for naming the chiral centers and the geometric isomers, for example E or Z alkenes, and the substituents on a chiral carbon are assigned priority based primarily on the atomic number of the atom directly bonded to the carbon atom. That is very important. You have to think about the atomic number of the atom which is attached directly to the chiral carbon center. Very important, that point. And here you can see a table kind of thing where in the left hand column you see the atom or the group, and in the right hand side you see the reason for priority and the first point of difference, and which is considerable under the atomic numbers. And it begins with iodine having the atomic number 53, and at the bottom you can see hydrogen which is having the atomic number 1. And in between these two you see different functional groups where it can be the functional group can be a carbon containing group, and those carbon will be attached to the chiral carbon, and then you have the heteroatoms there then after attached with the carbon center further, like in case of COOH, CONH2, CHO, CH2OH, CH2NH2. Those are the functional groups I was talking about, where you have to first it is the carbon atom which is directly attached to the chiral carbon center, and then further there are heteroatoms. So these are a short list of substituents to be prioritized when we consider the RS nomenclature of a chiral molecule. Now, for the absolute configuration, R and S notations, how we should apply the Cahn-Ingold-Prelog rules to determine the RS nomenclature or the RS abbreviation on a chiral center. The first thing we need to do that we need to rank the atoms attached to chiral center according to atomic number. For example, for the compound, as I mentioned before, that 1-bromo-1-chloroethane, that molecule, you can see the 4 attached groups are bromine, chlorine, hydrogen, and a methyl group. That means a carbon center, carbon attached with the chiral carbon center in the middle. So the priority group should be sequenced as follows: bromine should be greater than chlorine, chlorine further greater than carbon, carbon greater than hydrogen. So these are sequence of 1, 2, 3, 4. Now what we need to do, we need to rotate the molecule in such a direction that the substituent 4 or the priority group 4 is in the back or in the dashed line or away from the viewer. All these are same. For this compound which is given here, this is the hydrogen atom which is the 4th one in priority, is already placed in the dashed line, that is away from the viewer. So in that case we don't need to rotate the molecule any further. Here you can see for molecule A or the compound A, the clockwise rotation or the path from 1, 2 and 3 give the chiral center assigned as R. For compound B, where the 4th priority group hydrogen is also again here in the back side or in the dashed line. So in that case, you don't need to rotate the molecule any further, but you need to proceed from 1, 2, and 3 this direction. Now for this B molecule, this direction of 1, 2, and 3 leads to counterclockwise path, and therefore this is assigned as S. Now another question, how do we determine R and S when the fourth group is in front or on a wedge position? So far in the last slide, we've seen the fourth group is already in the back side, that means away from the viewer, so we don't need to do anything. We just need to follow the 1, 2, and 3 sequence, and we assign the term R or S for the chiral center. Now what happened if the fourth group is in front towards the viewer, and that means that is in a wedge orientation? Now consider 1-fluoroethanol here, and for assigning the R and S nomenclature for this chiral carbon, there are two options. First option is rotation. As I said before in the previous slide, that we need to rotate the molecule. Now first we need to prioritize the 4 group. You can see for 1-fluoroethanol, fluorine will get number 1, OH hydroxy group will get number 2, carbon of the methyl group will get number 3, and hydrogen atom will get the 4th priority. Now for number 1, rotation of the molecule 1-fluoroethanol, if we flip the entire molecule by 180 degree, and that means out of the plane of the page, you can see the I have tried to show here the rotation the way it should be thought in the mind, and then you end up with something in the right hand side. You can see where now the hydrogen atom, the 4th priority group, is presented in the dashed lines, that is it has went further away from the viewer. So now this is applicable for the assigning. Okay, so now if we assign that with the priority order 1, 2, and 3, it seems the path goes in a clockwise fashion. That is, it should be assigned as R. Okay, so this is one way that you flip the molecule, entire molecule by 180 degree, and it should be out of the plane of the page, so that you can keep the hydrogen atom, the 4th priority group, at the away from the viewer or away from yourself on the page. So this is when you get the final molecule, this is the same molecule that is drawn from 2 different perspectives. For example, from the left hand one of 1-fluoroethanol, this seems that you are looking at the molecule directly from the screen, and if you go in the back side of the screen, you will find compound, the other one, where hydrogen will be in the back side and OH group will be towards the viewer if you go into the back side of the screen. So this helps the flipping of entire molecule 180 degree lead to the same molecule drawn from 2 different perspectives. So this is one way of representing or assigning R or S. Second one is we need to apply the opposite rule. Okay, we just need to apply the opposite rule. How can we do that? We can get the same result if we just apply the opposite of the normal RS rule. Okay, just this is very tricky one. As I said, that I will be talking about some easiest tricks. So this is one of the trick, that whatever way they are, like you can see the 1-fluoroethanol, the way represented, the 4th priority group is in the wedge form. So we just keep going on or proceed from 1, 2, and 3, and it goes like counterclockwise, right? If we go like this way, it goes counterclockwise. So in that case, it looks like S, and the 4th priority group hydrogen is pointing out of the plane of the page. So the flip, now if we flip the result, as I said, we need to do the opposite of the normal RS rule. Now if we flip the result, so in that case, the flip S will give us the real configuration R. Okay, so whatever we get from 1, 2, 3 rotation, we just change it to the opposite one, or we take the other one. Did you get me? So that means that if we get 1 2 3 here, the counterclockwise, it gives you S. Finally, as the fourth group is pointing out of the page, outward or outward of the plane of the page, so we will term this as R. Now this is almost always easier than the first version, to me at least, than rotating the molecule. So this is the normal one. If you are given a molecule with a chiral center in the flying wedge formula, and the fourth priority group is toward the viewer, not from the away from the viewer, that is in the wedge form, then you proceed for 1 2 3. Let's see what the assignment gives, and you just change to the other one. If it is S, you go for the R. If it is R, you go for the S. That will give you the real configuration. Another option is how to determine RS when the fourth priority group is on the plane of the page. This is another option. So we take an example as 1-fluoro-1-methoxyethane. Okay, so this is one example where you can see the fourth priority group hydrogen is on the plane of the page. There are 3 steps for this one. First, we need to swap the priority group, the fourth priority group hydrogen, with whichever group is in the back, that is noted or denoted with the dash line. Okay, now here this is the methyl group. So we need to swap the fourth priority group hydrogen with methyl group here first. And that will, with the single swap, we will get the version as you can see after the step 1. Then we need to determine the R and S on the swapped chiral center. What we have got, now we need to go through that one. So after step 2, you see in the right hand part the molecule, and we go for the priority 1 2 3 4, and with the 1 2 3 we see that it's clockwise proceeding, or therefore it appears to be R from that sense. Okay, now in the step 3 we need to flip the result since we did a single swap. Okay, I will be coming very soon into the double swapping or double conversion. So as we have did a single swap, the true configuration of the chiral center is the opposite what we obtained in step 2. Okay, so as we have obtained the clockwise appearance or proceedings and to be assigned as R after step 2, then in that case we need to flip our R result from step 2 to give the true configuration S. So for 1-fluoro-1-methoxyethane in the given molecular structure, it should be finally termed as S1-fluoro-1-methoxyethane. I hope this is clear. Here comes the double switch and orienting a tetrahedron. As I said just a couple of seconds back, that interchanging any two groups inverts the stereochemistry. So switch the lowest priority group to the desired position. So that means if the fourth priority group is on the page, you need to exchange that or swap that or interchange that with the group which is in the represented in the dashed line. Okay, then we switch any other two groups, keeping the fourth priority group in the dashed lines or away from the viewer or in the back side. We need to switch any two other groups. The double switch does not change the stereochemistry any further, and then we go for 1 2 3 the priority group, and we can assign the chirality of that carbon of the chiral carbon center. For example, there are 2 examples here. The first one, you can see hydrogen atom and carboxylic acid groups. Hydrogen atom is on the plane of the page and carboxylic acid group is in the back. So we need to first interchange hydrogen and COOH. Okay, so this will invert the stereochemistry and you get the structure which is represented in the middle of the first row. And then any two groups can be interchanged, and for example we switch among the OH and COOH further. Okay, so then we need to go for 1 2 3, the way proceeding, and that shows that this goes in a clockwise direction, and your fourth group now is in the dashed lines represented. So the double interchange or the double interchange of the groups will definitely gives you retains or giving the retention of original stereochemistry, and whatever you assign 1 2 3 here will be the final one or the real configuration. Similarly, if you look at the second example, the fourth priority group here should be the fluorine. Now we need to interchange the fluorine with iodine, because currently iodine is in the dashed line or in the backside from the viewer. So the fluorine, the fourth priority group, fluorine need to be interchanged with iodine. You see the middle structure of the second row where the inversion of stereochemistry has taken place. And now we can interchange any two groups except the fourth group, obviously, and we interchange the iodo and the bromo groups, and that will lead to the structure you can see in the right hand side in the last structure of the second row. And you can go with the 1 2 and 3, and that goes in the anti-clockwise direction or the counterclockwise direction, and it retains the original stereochemistry. So therefore the configuration of that chiral carbon should be S. Next one comes Fischer projections. So the representation of a three-dimensional molecule as a flat structure is presented by the Fischer projection formula. A tetrahedral carbon here is presented using just two crossed lines. As you can see over here, that the junction of the crossing of the two lines, vertical and the horizontal one, will be treated as the carbon center, and at the end of the lines will be placed the substituents. And this one is quite equivalent to the shape you can see in the right hand side, where the vertical bonds are to be represented as away from the viewer or in the back side or below the plane, and the horizontal bonds are to be termed as in the wedge form, that is towards the viewer or above the plane. So the horizontal lines, as I said, which is towards you, is coming out of the plane or page, and the vertical line is going back. Now there are two examples in the flying wedge formula, and they have been transferred or transformed into the Fischer projection formula. With the first one, you see the chiral carbon is attached with 4 halogen atoms, fluorine, chlorine, bromine, iodine, and then they are transformed into the Fischer projection formula. And here you need to find that the fluorine and bromine, which were represented on the plane of the page, has been placed vertically. Okay, then the iodo and chlorine atoms or groups are placed accordingly. Similarly, if you look at the second example, hydrogen and COOH or carboxylic acid group has been placed vertically because they appear in the flying wedge formula, they appear on the plane of the page. And then OH and CH3 groups are placed accordingly. Now here the question arises how to put the rest two groups, which one is in the dashed line, one is in the wedge line. Now what I prefer, that I take it the groups as clockwise, and when I put into the Fischer projection formula, I put it in the anti-clockwise fashion. Next comes the manipulation of the Fischer projection. How do we do that? Now rotating a Fischer projection by 180 degree will eventually retain the configuration. Okay, so you see the same compound with 4 halogen atoms. If we rotate the compound by 180 degrees, so all the atoms or substituents will change its position. That means fluoro will come from the top to the bottom, bromine will go from the bottom to the top. Similarly, the iodo and chloro will exchange their positions. Okay, this is a simple manipulation by 180 degree to keep the 180-degree rotation will keep the configuration as it is. However, rotating a Fischer projection by 90-degree will invert the configuration. You see the two structures, and it has been rotated by 90-degree only, so they inverse the configurations, and those molecules are stereoisomers, are enantiomers in relation. Another option is if one of the group of a Fischer projection is held steady and the other three groups can be rotated clockwise or counterclockwise without altering the configuration. Then they will lead eventually to identical molecules. Okay, so one group need to be held steady. So these are simple manipulation of Fischer projections to convert one molecular structure or formula or configuration to the other one. Now, how to assign the R and S configurations to the Fischer projections? The rule says that we need to assign the priorities to the four substituents according to Cahn-Ingold-Prelog rules, the CIP rule. So this is the first thing we need to do in all cases. Whatever you do for the configuration assignment, you need to do that. The second one is you need to perform the two allowed manipulations of the Fischer projection to place the lowest priority group at the top or at the bottom. What does that mean? That means you need to keep the lowest priority group away from the viewer or below the plane or in the dashed line. This is very important. Third, if the priority of the groups going from 1, 2, 3 are clockwise, then assign the center as R. Mind it, we have kept the fourth priority group in the at the top or at the bottom, that means on the vertical line. Then only if the other priority groups 1, 2, 3 are leading to clockwise orientation, then assign the center as R. If the 1, 2, 3 are counterclockwise, then you need to assign the center as S. For example, here we need to hold steady one group. We have said that, and say we keep the CH3 group hold steady. And the fourth priority group, hydrogen, for this molecule of example here, we put that at the top. We place that hydrogen atom at the top. So in the right hand side, the molecular orientation in the Fischer projection now becomes in that way. Okay, so now if we go with 1, 2 and 3, we proceed keeping the fourth priority group hydrogen in one of the vertical positions here in the top, then that lead to clockwise orientation and the assignment of the chiral center to be says as R. The configuration of the chiral center will be R. What happens when molecules with more than one stereo center? For those cases, how to assign the R and S configurations? Now, if a molecule has one stereo center, it exists as R and S isomer, which are enantiomers eventually. And if a molecule has two stereo centers, each of them can exist as R and S, independent of the other center. So it does not depend on the other center, whether it is R or S, it can be either way. And it says that the maximum number of stereoisomers of a molecule, or for a molecule having n number of stereo centers, will be 2 to the power n. Now, if we consider the molecule 2-bromopentane, you can see the two chiral centers where the two bromine atoms are attached, and it has the two chiral centers, and therefore 2 to the power 2, that means there can be 4 stereoisomers for 2,3-dibromopentane molecule. It can be 2R, 3R, 2R, 3S, 2S, 3R, or 2S, 3S. All these 4 stereoisomers are possible. Okay. Now, 2R, 3R, and 2S, 3S, these two isomers are enantiomers, and the other one, the 2R 3S and 2S 3R, those are identical isomers. 2R 3R isomer is a diastereomer with 2R 3S and 2S 3R isomer. Similarly, 2S 3S isomer is diastereomer of 2R 3S and 2S 3R isomers. Here some the stereoisomers of 2,3-dibromopentane, it's represented in that way. You can see the molecular structures. They are in the first two structures, you see they are assigned as RS and SR, and they are mirror images to each other, however non-superimposable. So those are enantiomers in nature. And however, if you go along the column, you will see these two stereoisomers are diastereomeric in nature because they are not related to mirror image relationship to each other by any way. So from here, for 2,3-dibromopentane, you can easily understand what are the among the four stereoisomers possible, what are the relationship of the enantiomers, and what are the diastereomeric relationship between the four stereoisomers. Now we talk about the 2,3-dibromobutane. Now it is a little bit interesting for this compound. Here the RS and SR isomers are eventually the identical molecules, and the diastereomer is called here as mesoisomer because this is an achiral molecule. And this results because you can easily find a plane of symmetry present in the isomer going in between the 2 and 3 carbon centers. Okay, so dividing the molecule into two equal halves. So it should be an achiral molecule. Thus, although the maximum number of stereoisomers can never be more than 2 to the power n, in fact, the actual number could be lower than that. And here also for 2,3-dibromobutane, you can see from the Fischer projection formulas the four possible stereoisomers, the two which are diastereomers to each other. Similarly, the pair of enantiomers of this stereoisomer of 2,3-dibromobutane as well. Here I have shown some mesodiastereoisomers, some alcohols, for example 2,5 2,4 dihydroxypentane, 2,3,4 trihydroxypentane, bute 2,3 dihydroxydioic acid, and 1,3-dichlorocyclohexane compounds, where with the dotted line it has been represented the plane of symmetry within the molecule, and therefore these stereoisomers are achiral and they are termed rather as the mesodiastereomers. Now another important point is for the molecules where the chirality without a stereocenter. So there the carbon center don't have four different groups attached to it, but still the chirality generates within the molecule. These are the biphenyls, commonly known these molecules. For example, if you see if the biphenyls are no substitution is there, that should be a symmetric biphenyl, and this is achiral. And if the ortho positions of the either phenyl ring of the biphenyl system are substituted, they are asymmetric. Okay, so that can lead to chirality. Even if the X group that shown over here at the ortho position of the phenyl rings of the biphenyl systems is a very small group, the single bond connecting the two phenyl rings would undergo easy rotation, and therefore it will result in racemization. Now the chirality can be generated when the rotation is restricted, okay, within around the single bond. So in that case, the X substituent need to be some bulky groups. So by means of steric hindrance, they restrict the rotation around the single bonds, and therefore chirality generates. And this phenomena is known as atrope isomerism. For example, it's been given an example where you can see the ortho positions are substituted with nitro and carboxylic acid groups. Now these two stereoisomers are mirror images to each other. However, they are non-superimposable. So these are pair of enantiomers. And you see how these enantiomers, the chirality of these enantiomer have been assigned, and this has been represented in either way with the Fischer projection. You can see the nomenclature from 1, 2, and 3 and the fourth priority group, and how they lead to the nomenclature for the left hand side, that compound as R, and from the right hand side compound as S. So thank you guys for watching my channel TG Chemistry, and keep watching and subscribe my channel to see more videos like these, which are important for the students from class 11, 12, and after that for higher educations as well, and also for the UG and PG students, for which I always bring some important topics so that they can get some help during the exams. Thank you.